So last class we have to be discussed drift current and diffusion currents. Today we have to be discussed charge density in semiconductor. So charge density in semiconductor. So we have to calculate the minority carriers. For example, so when it is in N type, so what are the majority carriers? Electrons are the majority carriers. Electrons are majority carriers. Holes are minority carriers. Holes are minority carriers. Suppose it is p type. What are the majority carriers? Holes are majority carriers. Electrons are minority carriers. So here in this in p type, so it is called as acceptor ion. In n type, so this one is called donor ion. In n type, it is called as donor ion. So both are electrically neutrality. It has electrical neutrality. When material has electrically neutral, so when we want to discuss electrical neutrality, when it is electrically neutral, positive charge is equal to negative charge. So what is the positive charge? So holes plus donor ions. Holes plus donor ions is equal to electrons plus acceptor ions. Electrons plus acceptor ions. So calculate minority concentration. Here, what is the formula for that? For calculate minority concentration, what is the formula for that? So N into P is equal to Ni square. So square of intrinsic concentration. In N type, donor ion is equal to number of electrons. So initially we have to be assumed a P approximately equal to 0. According to mass action law, what it will become? Nn Pn is equal to square of intrinsic concentration. So same way, Nd Pn is equal to square of intrinsic concentration. So suppose we want Pn, what it will be? So square of intrinsic concentration by donor. So here in P type, same way what it will become? Acceptor is equal to holes. N approximately equal to 0. So NP PP is equal to Ni square. NP is equal to Ni square by PP. So intrinsic concentration by acceptor ion. So what is drift current density? So now we want to see the drift current density. See here, drift current density. So we know very well. So I is equal to charge by time. So that is Q by T. I is equal to charge by time. That is I is equal to Q by T. So we write it as E by T also. So when we have to take an as certain volume of material. So here are the electrons in that electrons. What is the current flowing here? I is equal to number of electrons Q by T. So current density J is equal to I by A. So what is I? I is equal to NQ by T. What is I? NQ by T by A. So substitute the I NQ by A T. So what is T? As per drift velocity Vd is equal to so L by T. So in this T is equal to L by drift velocity Vd. So substitute T is equal to L by Vd. What we will be get? So when we substitute N Q, so substitution of T, what you have to be substitute? L by Vd. So that's why drift velocity by A into L. So electron per unit volume. So this will be what it gives to you. Electron per unit volume, nothing but N. So J is equal to N into Q into drift velocity Vd. So J is equal to what is NQ? We call it as charge density. So this is charge density. So rho Vd. So NQ Vd. Vd means so this one is rho. So charge density Vd means mu into E. So N Q mu E. So J is equal to all these three is called as conductivity sigma. Sigma E. Current density J is equal to sigma E. Current density J is equal to sigma E. So here the drift current density J is equal to sigma E. So here for this N type N into Q into mu N mobility of electrons. So same way for P type P into Q into mobility of holes. What is diffusion current? So current density due to electrons. What is diffusion current? current density in electrons Jn is equal to Q mu n dn by dx with respect to distance the concentration. So here same way Jp is equal to minus Q mu p dp by dx. So finally, so here J current density J is equal to diffusion current plus drift current. Diffusion current plus drift current. Finally, J is equal to diffusion current plus drift current. So here we know very well. Next relationship is Einstein relationship. So next one, Einstein relationship. In that, diffusion constant dn, diffusion constant dn by mobility constant mu n is equal to, so diffusion constant of electrons is equal to diffusion constant of holes dp by mobility of constant electrons is equal to mobility of constant holes. So that is equal to Vt, nothing but volt equivalent temperature. So what is the formula of Vt? Vt is equal to Kt by Q. So nothing but, so at 300 degrees Kelvin by 11,600, it gives approximately 26 millivolts. So here dN by mu n is equal to dN by mu n is equal to Vt is equal to 26 millivolts. So here the Einstein relationship. So dN by mu n is equal to dP by mu p is equal to Vt, that is nothing but 26 millivolts. 26 millivolts. So see the mass action problems. So here the problems of mass action law. So in that, the first one, if drift velocity of holes, if drift velocity of holes under field gradient of 100 volt per centimeter is 5 meter per second, what is the mobility? So what is the mobility? So what they have to given data? So for given data in this problem, they have to given electric field is equal to how much? Field gradient means electric field 100 volt per centimeters. 100 volt per centimeters. So this is 5 meter per second is drift velocity. So what it is called as? Drift velocity is how much? So Vd is equal to 5 meter per second. So what we want to find out? Mobility. Mu is equal to how much? So here, what is the relationship between drift velocity and mobility. So Vd is equal to mu e. Vd is equal to mu e. We want to find out the mobility. So that is Vd upon E is equal to, what is the Ed value? 5 meter per second. 5 meter per second upon 100 volt per centimeter. 100 volt per centimeter. So we know very well 1 meter is equal to 100 centimeters. Same way, we want to convert 5 centimeter per second into 100 by 100 volt per centimeter. So we have to be get how much value? 5 centimeter square per volt second. So what will you get? Mobility is equal to 5 centimeter square per volt second. So go to the next problem. The carrier mobility in semiconductor is the carrier mobility in a semiconductor is zero point 0.4 meter square per volt second. Find diffusion constant. Find diffusion constant at 300 degrees Kelvin. So what is the diffusion constant? What the given data? So the given data is zero point 0.4 meter square per volt second. What is that? Mu. The carrier mobility in a semiconductor is zero point 0.4 meter square per volt second. That means mu is equal to zero point 0.4 meter square per volt second. What is diffusion constant? What they want? Find diffusion constant. So they need diffusion constant. So here we don't know N type or P type. Here we don't know the semiconductor is N type or P type. According to Einstein relationship, we know d by mu is equal to Vt. D by mu is equal to Vt. Just now we discussed Einstein relationship, isn't it? So d by mu is equal to Vt, thermal voltage. So what is here? D is equal to mu into Vt. Vt we know, d mu we know. So we are easily find out the d. D is equal to mu into Vt. Mu into Vt. What is the mu value? Zero point 0.4 meter square upon volt second into 26 millivolts. How much you get? 10.4 into 10 power minus 3 meter square upon volt second. So here in Einstein relationship, depending upon the formula, d by mu is equal to Vt. We get the d is equal to, so what we want to find out? Diffusion constant. So that diffusion constant is equal to 10.4 into 10 power minus 3. So now we have to be discussed another problem. So in that next problem, in a p type silicon. In gate examination, this will be asked in 1 mark question. So in a p-type silicon sample, the whole concentration is 2.25. How much? 2.25 into 10 power 15 per centimeter cube. The intrinsic carrier concentration is the intrinsic carrier concentration is 1.5 into 10 power 10 upon centimeter cube. What is the electron concentration is? What is the electron concentration is? So according to mass action law, use it to find minority carrier concentration. What is the formula? N into P is equal to square of intrinsic concentration. So square of intrinsic concentration. So N is equal to square of intrinsic concentration by upon P is equal to. So what is intrinsic concentration? So already they have to given to us 1.5 into 10 power 10 per centimeter cube. So that will be 1.5 into 10 power 10 whole square by how much? What is the whole concentration? 2.25 into 10 power 15. So 2.25 into 10 power 15. How much we get? So square of intrinsic concentration value is 2.25 into 10 power 20 per. So same way the whole concentration. So here, what is here? So whole concentration is 2.25 into 10 power 15 per centimeter cube. So how much you get? So finally we get the value 10 power 5 per centimeter cube. 10 power 5 by centimeter cube. So what is the next problem? So next one is the intrinsic carrier density. The in 1997 this question asked the intrinsic carrier density at 300 degrees Kelvin is 1.5 into 10 power 10 per centimeter in silicon. For n-type silicon, doped to 2.25 into 10 power 15 atoms per centimeter cube. The equilibrium electron and hole concentration is how much? The electron and holes concentration is how much? So this was asked in 1997 2 marks question. What they given to us? So intrinsic carrier density, how much they given? 1.5 into 10 power 10 per centimeter cube. Dopant atoms, Nd is equal to 2.25 into 10 power 15 atom per centimeter cube. By equilibrium, what is the N and P? So silicon doped with phosphorus arsenic is fifth group of elements. Suppose it is doped with boron, so that is third group of element, P type, nothing but P type. Phosphorus atom donate one electron because of fifth group of elements are donors. So it donate one electron. So total number of electrons N is equal to 2.25 into 10 power 15 electrons per centimeter cube. So here N is equal to number of charge carriers. N is equal to number of charge carriers. Same way P is equal to Ni square by N. So what is Ni? Means in square of intrinsic concentration 1.5 into 10 power 10 per centimeter cube. So that value you have to write here 1.5 into 10 power 10 whole square by means upon 2.25. What is the n value? 2.25 into 10 power 15. 2.25 into 10 power 15. So what you get here? The square of that one is 2.25 into 10 power 20 per centimeter. So 2.25 into 10 power 15 per centimeter cube. So how much you get? So here 2.25 get cancelled. So 10 power 20, 10 power 15 how much? So because of minus to 10 power 5 per centimeter cube. So next question is, in an intrinsic semiconductor, in an intrinsic semiconductor, the free electron concentration depends on the free electron concentration the free electron concentration depends on option A, effective mass of electrons only, effective mass of electrons only, option B, effective mass of holes only, option C, temperature of the semiconductor. So this question asked in GATE as 2 marks question. The width of the forbidden energy band of the semiconductor. Width of the forbidden energy band of the semiconductor. So what is the answer? We know very well. According to mass action law, N into P is equal to Ni square. Means intrinsic square of intrinsic concentration. So here Ni is intrinsic concentration, P hole concentration, N electron concentration. So what is the relation of square of intrinsic concentration is proportional to T power 3. So Ni is proportional to T 3 by 2. So for intrinsic semiconductor, N is equal to P is equal to intrinsic concentration. So this will be proportional to T power 3 by 2. So nothing but it will be depends on temperature of the semiconductor. C is the answer. So temperature of the semiconductor. So it will be depends on temperature of the semiconductor. So next problem. A silicon PN junction is forward biased A silicon PN junction is forward biased with a constant current at room temperature when the temperature is increased by 10 degrees centigrade, the forward bias voltage across the PN junction. Forward bias voltage across the PN junction. Before going to discussion of this problem, we must know the PN junction diode. So in PN junction diode, why the name is called diode? Whenever device having two terminals, it's a die, is called a diode. So whenever device having three terminals, it is called as triode. For example, BJT, SCR, FET, like that. Suppose the device having four terminals, that is called tetrode, silicon control switch. So those are called as tetrodes. So diode is a active device or passive device? Diode is a passive device. So normal diode cannot produce any voltage. So that's why diode is a passive device. So diode used as switch. So diode is a unipolar or bipolar device. So diode is a bipolar device. What it is called as? So what is our diode is a active device or passive device? It is a passive device. So it used as a switch. It used as a switch. It is unipolar or bipolar device. It is a bipolar device. Unipolar means current conduction due to only majority carriers. So bipolar means current conduction due to two types of charge carriers. That is called bipolar devices. So in diode is also one diode is unipolar. So that is Schottky diode. Current due to only electrons. The special purpose diode is Schottky diode. So that is unipolar. It is in that current due to only electrons. Diode is a unidirectional, bidirectional. Diode is a unidirectional. So diode is a unidirectional. We know very well the symbol of PN junction diode. So that symbol is, this is the symbol of PN junction diode. So why the symbol is like this? In electronics, we follow the current is conventional. So diode construction is, so this one is plus, minus, nothing but diode construction is P and N type. So this one is P type. So this one is N type. Holes move P side to N side. So that is conventional current. So that will be shows this here. Okay. So this will be indicates it block the current. That means it will not flow cathode to anode. It will not flow cathode to anode. So diode is a controlled device or uncontrolled device. So it is a uncontrolled device. So finally, what is diode? So diode is a two terminal. So diode is a two terminal passive bipolar uncontrolled electronic device. Uncontrolled electronic device. Where we have to be used diodes. Diodes can be used as rectifier circuit, clippers and clampers, resistors, function generators, like that. So suppose PN junction diode is, it is in unbiased condition. Suppose PN junction diode is unbiased condition. What happen? In unbiased condition, so unbiased means you don't give any supply for that. So PN junction diode in unbiased condition. So this is called P type, N type. So this is metallurgical junction. So in P type, majority carriers are holes, minority carriers are electrons. So in N type, majority carriers are electrons, minority carriers are holes. Minority carriers are holes. So here in silicon, one side pentavalent impurities are added. So that is called N type. One side trivalent impurities are added. So that is called P type material. So in P type, majority carriers are holes, minority carriers are electrons. In N type, majority carriers are holes. So this is called metallurgical junction. So what happened when we have to dope the one semiconductor material? So immediately it will be form the junction. So here this is P type. So this one is N type. What happened? Majority carriers are holes. Here majority carriers are electrons. Minority carriers are electrons. Minority carriers are holes. So here these are the immobile ions will be formed here. So here immobile ion. Immediately it will be forms. So this region is called depletion region. This region is called depletion region or space charge region or transition region or transition region. What is depletion region? Mobile charge carriers are depleted away. So here there is no charge carriers. So it acts as a barrier. So it will be acts as a barrier. It will not allow to flow the electrons or holes p side. I mean, suppose it is p type, it will not allow the holes p to n side and n side to p side. So here the order of depletion region is zero point 0.5 micrometers. So what is the barrier height? Not a distance, it is a potential. So for this, zero point 0.7 volts for silicon, zero point 0.3 volts for germanium. So here the order of depletion region is zero point 0.5 micrometers, and so it has zero point 0.7 volts for silicon, zero point 0.3 volts for germanium. So actually what you are given, this one is the this potential barrier. So holes are here, electrons are here. So it is the this one is the barrier. It will not allow the holes to electrons, electrons to hole. This barrier will be suppressed. That means when you are given more than this cut-in voltage, then only it will be suppressed and the holes and electrons are move one place to another place. So that barrier built-in potential VBI is equal to VT natural logarithm of ND NA by Na square. Acceptor concentration. So donor concentration. So this one is donor concentration, acceptor concentration, intrinsic concentration, square of intrinsic concentration. So this will be depends on temperature. So this is depends on temperature. So that means barrier potential depends on temperature. So barrier potential depends on temperature. So when temperature increases, barrier potential decreases. So that will be decreased approximately 2.5 millivolts per degree centigrade. So this will be shows to you dVBI by dt equal to minus 2.5 millivolts per degree centigrade. So every rise in 1 degree centigrade, it reduces the minus 2.5 millivolts. So diode is unbiased. What is the current? The current is 0. Diode is unbiased. The current is 0. Why? Because the majority carriers cross in the junction is equal to minority carriers cross in the junction. So that is nothing but diffusion current is equal to drift current. So that is nothing but diffusion current is equal to drift current. Suppose when you are applying the voltage, so this PN junction diode is forward bias. Suppose this PN junction diode is forward bias. So when you are applying voltage, so what happened? So here when electrons move from here to here, so that is called injected minority carriers. What it is called? Electrons move from here to here. That is called injected minority carriers. So that is called injected minority carriers. Suppose holes will be go here to here. That is called injected minority carrier. Holes are injected minority carriers. Here applied voltage positive terminal of battery is connected to the P type. So applied voltage negative terminal is connected to the N type. So applied voltage reduces the barrier effect. So voltage exceed the barrier voltage. Electrons diffuse, move N side to P side. Holes diffuse to move P side to N side. So in P type electrons are majority carriers. Those are called injected minority carriers. In P type electrons are minority carriers. So we have to be observed here. In P type electrons are minority carriers. That minority carriers electrons are called injected minority carriers. So what happened in forward bias? So in forward bias PN junction diode, current is due to mainly diffusion current. In forward bias, current is due to mainly diffusion current. Because we applied voltage is only for reduce the barrier height. So the current is due to diffusion. So what you have to be apply the voltage will be only for to reduce the barrier. So only for to reduce the barrier height. So it is due to diffusion. So it will not the collision. So it will not the reverse current. So only we have to apply the to reduce the barrier height. So that's why in forward bias the current is diffusion current. In forward bias current is due to majority carriers, that is diffusion current. So what are the characteristics for this forward bias? This forward bias. So here this one is voltage. So this one is current. So voltage is greater than built-in potential. The current started to increase. So here the cut-in voltage has, after that it will be increased. So here cut-in voltage. So this is called cut-in voltage, new voltage or threshold voltage. So what is the diode current equation? Diode current equation I is equal to I naught into e power v by eta vt minus 1. So I is equal to I naught into e power v by eta vt minus 1. So I naught is reverse saturation current. V is applied voltage. Vt is volt equivalent temperature. So we know very well eta is equal to 1 for germanium, 2 for silicon. 1 for germanium and 2 for silicon. In reverse bias, what happened? In reverse bias, the current is equal to minus I naught. So finally, in forward bias, what you have to be observed? So the width of the depletion is reduced. So when it is forward bias, what happened? So the p-type material is, I mean, holes are try to go this side, electrons are try to come this side. So at the time, what happened? The width of the depletion region is reduced. It acts as a closed switch. So when current flows, that means what? I is equal to V by R. So for in forward bias, current will flow. So that's why when current will flow, what about resistance? Resistance offers low resistance. Okay. So here diode in forward bias, it offers the resistance. So there are two types of resistances are there. There are two types of resistances are there. Those are static resistance and dynamic resistance. Static resistance and dynamic resistance. What is static resistance? What is the formula for static resistance means? So VDC by IDC. We know very well I is equal to V by R is equal to V by A. So that is static resistance means V by I is DC. DC voltage, DC current. What is dynamic resistance? So dynamic resistance RD is equal to change in voltage by change in current. Change in voltage by change in current. So that RD is equal to dV by dI. That RD is equal to dV by dI. So I is equal to I naught into e power V by eta Vt minus 1 with respect to voltage differentiate it. What happened? So this drain resistance is equal to eta Vt by I. So when we want to find out this RD, this is proportional to 1 by current. So eta is constant, Vt is constant, Rd depends on inversely proportional to the current. Rd is depends on inversely proportional to the current. So here in silicon in examination they are asking, they given to you silicon PN junction has silicon PN junction has 5 volts. So it is in forward bias. The current is 13 milliamperes. What about drain resistance? So what is the formula for drain resistance? RD is equal to eta Vt by I. Okay, eta Vt by I. So here eta is silicon. So just now we discussed. So germanium is 1, silicon is 2. So that's why, so 2 into Vt means 26 milli by current is already they gave 13 milliamperes. 13 into 10 power minus 3. So how much you get? 4 ohms. So this drain resistance is 4 ohms. So diode in forward bias, it offers resistance. There are two types of resistance are there: static resistance and dynamic resistance. Static resistance and dynamic resistance. So according to that, so in previous we have to be go for problem. A silicon PN junction is forward biased. A silicon PN junction is forward biased with a constant current at room temperature. The constant current to room temperature. When the temperature is increased by 10 degrees centigrade, the forward bias voltage across the PN junction. Across the PN junction, how much? It is increased by 60 millivolts or decreases by 60 millivolts or increases by 25 millivolts or decreases by 25 millivolts. What is the answer? So just now we have to be discussed. It will be decreases 2.5 minus 2.5 millivolts per degree centigrade. Anna. So what happened here? So dV by dt is equal to minus 2.5 millivolts per degree centigrade. For 10 degree centigrade, voltage across PN junction will be decreases by 25 millivolts. So here, how much? 25 millivolts. So in PN junction, so another problem is in a uniformly doped in a uniformly doped abrupt PN junction, the doping level of the N side is four times. N side is four times. The doping level of the P side, the doping level of the P side, the ratio of the depletion layer width, the ratio of the depletion layer width of N side versus P side is how much? Answers 0.25 or zero point 0.5 or 1 or 2. What is the answer? This question is asked in 2 marks. So, according to related to width of the depletion layer, N side doping is 4 times the doping level. Means ND is equal to 4 Na. ND is equal to 4 Na. So for that relation, Xn ND is equal to XP Na. So layer width of the N side versus to P side, what happened? Xn by XP Na by Nd. We know Na, what is Nd? 4 Na. 4 Na, the value is 0.25. So this is the answer. So this will be asking 2 marks. So next problem. In an abrupt PN junction, the doping concentration on the P side and N side are Na is equal to 9 into 10 power 16 per centimeter cube, and Nd is equal to 1 into 10 power 16 per centimeter cube respectively. The PN junction is reverse biased. The PN junction is reverse biased. The total depletion width is 3 micrometers. The depletion width on the P side is how much? The answers are 2.7 micrometers, zero point 0.3 micrometers, 2.25 micrometers, 0.75 micrometers. What is the answer? What they given to us in previous case, they are asking relation. So in this case, they are asking P side depletion region. So what they given? Na given 9 into 10 power 16, Nd given 1 into 10 power 16. At the same time, width. The total depletion width is 3 micrometers. They have to be given Na, Nd and width. So what is the value of Na? So Na is 9 into 10 power 16. Nd is 1 into 10 power 16. Width is 3 micrometers. So xp is equal to width on the p side. So what we want to find out? So width on the p side. What is the formula for that? Width on the p side is total width into nd by na plus nd. So total width into nd upon na plus nd. So xp is equal to what is the width of here? So the width of total depletion width is 3 micrometers. So 3 micrometers into nd value is 10 power 16. Na value is 9 into 10 power 16 plus 10 power 16. So when we common the 10 power 16, what happened? 1 plus 9 is 10. So that's why, so 3 micrometers into, so here when you common this one, what happened? 10 power 16, 1 plus 9 means nothing but 10. So 10 power 16 upon 10 into 10 power 16 means 1 by 10, 3 micrometer into 1 by 10. How much you get? Zero point 0.3 micrometer. How much you get? Zero point 0.3 micrometer. So width of the P side is 0.3 micrometer. Width of the total width is 3 micrometers. So total width to 3 micrometers అయినప్పుడు, so this total width means n type, n width to p width to. So p side width is how much? 0.3. సో అప్పుడు ఏమొస్తుంది 3 మైనస్ 0.3 ఎన్ సైడ్ విడ్త్ ఎంత అయిండొచ్చు 2.7. సో నథింగ్ బట్ హియర్ ద విడ్త్ ఆఫ్ ది ఎన్ సైడ్ ఈస్ 2.7. So the first one they are asking the relation. So next previous case they are asking the ratio, and in this case they are asking the p side depletion region. So they gave to us Na, Nd and width. That is total width. So they gave to us total width. So from that we have to find out the p side width. So p side width is 0.3. Total width is 3 micrometers. When you subtract this 3 minus 0.3, get the 2.7 micrometers. So we will be continue GNR diode next class.